would just like to look at a couple of arithmetic problems first so that I can get you familiar with the process of adding and subtracting rational expressions that do not have common denominators. Many people look at this 3 and the 7 and they just say the common denominator is 21, and they are correct. I'm going to write this down over here. The LCD, the least common denominator, is 21. These two numbers are prime numbers, and I was able to just multiply those together to get that common denominator. That's not always going to be the case, but let's just follow up and remember how we add these fractions now. This is the way I like to show this. I like to show that the 2/3 needs to be multiplied by 7 over 7 in order to get a denominator of 21. And so it will become 14 over 21. The 5/7 needs to be multiplied by 3 over 3 to get a denominator of 21, and it will become 15 over 21. These are called equivalent expressions. I'm going to say to you that when you add and subtract rational expressions that do not have common denominators, that you're going to need to factor the denominators first, then you're going to need to find the common denominator, then you're going to need to write an equivalent expression by multiplying by 1 those fractions that need to be, so that you can get these equivalent expressions, and then go ahead and add or subtract. In this case, I'll add, and I'll have 29 over 21, and if I could, finally at the end, I should simplify. This example is one where these are both prime, and we're going to be looking at some problems, some algebraic expressions that might look like this. 2 over 3x plus 5 over 7y. The common denominator between the 3x and the 7y is just the product of everything that you see there. And I'm not going to finish this problem, but I just want you to start to get a feel for this. This 3 times this 7 is 21, and x times y. That is the whole common denominator that we're going to be looking to get for these two fractions before I add. Very similar to this, I use everything in each of those because there's nothing common to either. This problem is a little bit different in that I've got a denominator of 12 and a denominator of 9. If I took their products, 12 times 9, and got 108 as a denominator, while that would be a common denominator, it would not be the least common denominator. You do not want to use anything but the least common denominator. For these two, here's two ways to go about getting that common denominator. One is to write a prime factor tree of each of these denominators. In the case of the 12, I'm going to first factor it into 2 times 6, and then I'm going to notice that the 6 can be factored in again into the prime numbers of 2 times 3, and I'll bring down that 2. In the case of the 9, its prime factor tree is 3 times 3. The least common denominator, please listen to those words. The least common denominator is found by taking the factors that occur in each of these denominators the greatest number of times. I'm trying to accentuate the word least common denominator and the greatest number of times. 2's appear in this denominator twice. 2's do not appear in this denominator at all. The greatest number of times is 2 times. 3's appear in this denominator as a factor once. 3's appear in this denominator as factors twice. I have to use them the greatest number of times they occur in a denominator, and that's twice. And so my least common denominator for these two numbers is 36. So what I'm going to need to do, and I'm not sure I'll finish this, but I'm going to need to multiply this problem, or this fraction, by 3 over 3 to get the denominator of 36. And I will need to multiply this fraction by 4 over 4 to get that denominator of 36. Same process for adding and subtracting rational expressions. Then I would just multiply the numerator or write an equivalent expression. And then here 5 times 4 is 20 over 36. And finally I would add 33 plus 20 is 53 over 36. And I do not believe that those are going to be simplified. This example has two different monomials as denominators. I'm going to look for the least common denominator first, and I'm going to do that by factoring these into their prime factorizations. So I'll ignore the x for a minute. 18 factors into 2 times 9, and 9 factors into 3 times 3. So the prime factorization of 18 is 2 times 3 times 3, and I'm going to put now here times x. 24 will factor into 2 times 12, but then I need to take the 12 further into 2 times 6, and the 6 further yet into 2 times 3. And now I'm going to bring down all the factors of 2, and finally I'll bring down that factor of x. The LCD in this problem will be found by taking the 2's and the 3's and the x's, the greatest number of times that they occur. The 2 occurs here once. It occurs here 3 times. I must take it 3 times. The 3 occurs here once. It occurs here twice. I must take it 2 times because that's the greatest number of times it occurs. And then finally, the x occurs here once. It occurs in this denominator once. The greatest number of times it occurs is once. I will keep it 1 time. And what I have then here is 8 times 9, or 72x, as my least common denominator. So finally, I'm going to take this 13 over 18x, and I'm going to multiply it by, it looks like 4, top and bottom, in order to get a 72x downstairs. And when I do that, I'll have a 52 over 72x. And then the next fraction, 7 over 24x, needs to be multiplied by just a 3, top and bottom, in order to make this denominator become a 72. And I'll have 21 in the numerator over 72x in the denominator. And now I'm ready to add. Looks like the numerators will add to be 73 over 72x. I cannot reduce this. This problem is complete. I want to subtract these 2 fractions, and I need a common denominator. I'm going to look at the factors that occur in each of these denominators. Now, they're monomials again, and if you need to look at them this way, you may. This is a times, and I'm going to write the b out like this. This ab cubed is a times b times b times b. And likewise, this is a times b. So the least common denominator here, again, is to take each factor the greatest number of times that they occur. The a occurs here once. The a occurs here twice. I need to take it 2 times. The b occurs here once. The b occurs here 3 times. I need to include in my common denominator a b cubed because that's the greatest number of times. And so the 8 over a b cubed doesn't quite have this denominator yet. I have to multiply by the factor that's missing. In this case, it's a factor of a that's missing, and this fraction will become an equivalent fraction of 8a over a squared b cubed. And then the next fraction, the 3 over a squared b, is missing, it looks like, a factor of b squared, because I already have b to the first power right here. A squared is already taken care of. So this fraction, the numerator, will become 3b squared over a squared b to the 3rd power. The denominators are now alike, and I can go ahead and add or subtract in this case, the numerators. There are not like terms in the numerator, so all I can do is put those terms together. It will read 8a minus 3b squared over the common denominator of a squared b cubed. And because I can't factor anything out of this numerator in order to simplify it with the denominator, I find that the answer is complete. The reason I include this problem in our video clip here is that the situation is similar to the last problem in that I have to find a least common denominator between the c's and the d's, and it looks as though that's going to be, again, to the least common denominator is the greatest number of times these factors occur. So the c occurs to the 2nd power, and the d occurs to the 2nd power. That's my least common denominator. So this fraction right here, 2c minus d over c squared d, c squared d, is missing a factor of d. So I need to multiply, and I'm going to put parentheses around this so that I don't forget to multiply top and bottom, in this case, by d. And that means that I have to distribute this times both of these terms in the numerator. So the first term will become 2cd, and d times d here will be a minus d squared over a c squared d squared. This is called the equivalent fraction. The next fraction, c plus d over c d squared, is missing a factor of c. This needs to be c to the 2nd power. So I'm going to multiply top and bottom of this fraction by c, but I'm going to be sure to put it in parentheses so that I distribute the c times each term in the numerator. So that'll be a c squared, and here I'll have a cd over the common denominator of c squared d squared. And now because I have common denominators, I'm ready to collect my like terms. It looks like I have some in the numerator. I have a 2cd and a 1cd. I'll put those together and call those 3cd. I believe I'm going to put my c squared term first for alphabetical order, and then this 2cd plus 1cd is 3cd, and then I'll put my minus d squared as my last term over c squared d squared. The only way this problem could be reduced is if I could come up with a factor in this numerator of c or d to reduce with this denominator. There is not a common factor of c in every one of these terms, nor is there a common factor of d in every one of these terms, so I can't take the greatest common factor out here in order to try to reduce it with downstairs. This problem is complete. When two fractions are being added or subtracted, and they don't share any common factors at all, and they can't be factored. In this case, it's monomial, while it is 5 times y, and this denominator is y minus 2. You have to think of that as a binomial. You can't think of that y separate. It is part of or with this term of y minus 2. Then the LCD becomes the product of those two items. In this case, 5y times y minus 2. It's almost as though they're both prime. It is that. That is the case. So this first fraction, 4 over 5y, needs to be multiplied top and bottom by the part that it's missing. In this case, it's missing a y minus 2 over a y minus 2. And in the process of writing what's called an equivalent fraction, you need to multiply the numerators out, and so you'll have 4y minus 8. But you don't bother to do this with the denominators. It's going to be tough to remember. You need to keep track of that. Only multiply the numerators out because you only add and subtract the numerators. And then the second fraction, 7 over y minus 2, it's missing, as part of its denominator, a 5y over a 5y. I'm going to be careful to think of that denominator as this binomial. Writing an equivalent expression for that one, 7 times 5y is 35y. I'm going to put the 5y in front, the y minus 2 downstairs. Again, I only multiply the numerators in writing these equivalent expressions, and now they have common denominators. Finally, what I'm going to do is in this case, I'm going to subtract, so I'll remember to add the opposite of that 35y. And 4y and a minus 35y is a minus 31y. And then this minus 8 will come along over the common denominator of 5y times y minus 2. If I could factor something out of these two terms in an effort to have one of these factors show up so that I could reduce it, I would. But there's not a common denominator other than a common factor other than a -1 that I could pull out of those. That wouldn't allow me to reduce with anything down here. I'm going to leave this answer as is. The process of adding and subtracting rational expressions involves this getting a common denominator. If the denominators can be factored, we should do that. And if they can't, I have to think of them as, in this case, individual binomials. Again, just like the last problem, the least common denominator for these two problems will be the product of the two binomials that exist in each of those denominators individually. So I have an x plus 3 and an x minus 4. That is my least common denominator. The first fraction then, x minus 2 over x plus 3, and now I'm going to put parentheses around all of these, needs to be multiplied by x minus 4. Top and bottom, because that's what it's missing in its denominator. I'm going to go ahead and clean that up. While I don't ever multiply the denominators through, I will always, in this case, FOIL the numerators. I'm going to do and collect the outside and the inside terms in my head. X times x is x squared. Then I have a minus 4x here and a minus 2x right there. They collect to be a minus 6x. And a minus 2 times a minus 4 is a positive 8. There's my numerator over a common denominator of x plus 3 times x minus 4. Next, I'm going to address the second fraction, which reads x plus 2 over x minus 4. Again, I'm going to put those in parentheses now because I see that it's missing a common factor of x plus 3. And I need to multiply top and bottom in order to keep the balance, in order to multiply this fraction by 1. I'll only FOIL the numerator. X times x is x squared. Then I'll have a 3x and a 2x. That adds to be 5x. And 2 times 3 is a positive 6. Over a common denominator of x plus 3 times x minus 4. I prefer to write these denominators in the exact same order, so I chose to use the commutative property of multiplication and reverse the order here. Now, because they have common denominators, I'm ready to add the numerators. So I'm going to collect my like terms. For example, these x squareds, they'll combine to be a 2x squared. This minus 6x and this plus 5x will combine to be a minus 1x. And this plus 8 and this plus 6 will add to be 14 over x plus 3 times x minus 4. Now, I might think about trying to simplify this. And the way I would do this could be my final answer, but maybe I need to simplify it. The way I would do it, would be to factor this trinomial into the product of two binomials. I do know, however, that in that process of factoring, because of this 14 right here, that what would go in the latter part of each of those binomials would either be a 2 and a 7, because their product is 14, or a 1 and a 14, because their product is 14. These two binomials don't end in a 2 or a 7, nor do they end in a 14 or a 1. So it makes no point for me to attempt to try to factor this trinomial when I can see that there is no way that I'm going to get either an x plus 3 or an x minus 4 here that I could simplify with these denominators. This answer is complete. This problem is finally going to take us into the type of problem that requires us to use the very first step when we add and subtract rational expressions, and that is to factor the denominators only. The problems that we've done up until this point have either been monomials or they have been binomials that don't match and can't be factored. In this case, I have the difference of squares here, and I need to factor that denominator so that I can find out what the least common denominator is. This denominator factors into x plus 5 times x minus 5. And this denominator right here can't be factored, and I'll put parentheses around it, expressing it as a binomial. So now, I'm going to write my least common denominator as the product of those binomials, the greatest number of times they occur in any one denominator. X plus 5 occurs here once, and x plus 5 occurs here once. One time is the greatest number of times that x plus 5 occurs. I will use that in my LCD. X minus 5 occurs here once. X minus 5 does not occur here at all. I must use it once because it occurs once in one of my two denominators. That's my least common denominator for these two fractions. So this first fraction, 4x over x plus 5 times x minus 5, is all ready to go. It's got the least common denominator. It's this fraction, the x over the x plus 5, that is missing a piece. And it's missing the x minus 5. And so I'll multiply top and bottom by that so that I can get this to have the common denominator. I will have to, remember, only multiply the numerators out so that I can add and subtract the numerators. Here, x times x is x squared, and x times a minus 5 is a minus 5x. Over this common denominator of x plus 5 times x minus 5. And over here I have the fraction that I began with, 4x over x plus 5 times x minus 5. I'm ready now to add, in this case, these two fractions. And so my first term will be x squared. There are no like terms to combine with this one, but this plus 4x and that minus 5x is a minus 1x. Over x plus 5 times x minus 5. Now while I see that I can factor the numerator, and I'm going to go ahead and show this time, I see that I can take a common factor of x out of both of those terms. It does me no good because nothing up here will be a common factor with what's down here whereby I could reduce. Either of these answers are good. I could leave it like this, and I could write it like this. Remember, you're going to be taking this test in a proctored environment, so whichever way you give me will be correct. This is an interesting problem because actually, the way it's written, when I factor these denominators, which is always my first step in an effort to find the least common denominator, I will find that I could possibly reduce this fraction. I think I'm going to leave it though in that process so you can see that process occur at the very end. So I do see, however, in this denominator that I have a common factor of 3. I need to remove that. In this denominator, I have the difference of squares. I need to write that as x plus 2 times x minus 2. And finally, I'm ready to state what my LCD is. The 3 occurs once, I must include it. The x plus 2 occurs once here and once here. I must include it just once. And the x minus 2 occurs once here and not at all over here. I must include it once. This is my LCD. I've got to make both of these fractions have that as part of their LCD. So the first one, the 3x plus 2 over the 3 times the x plus 2 needs to be multiplied by x minus 2 top and bottom. You've got to be careful right here. The whole numerator has to be multiplied by this x minus 2, which I'm using to create an equivalent fraction. And so I have to FOIL this. So 3x times x is 3x squared. Again, I'm going to do the inner and the outers in my head. 3x times a minus 2 is a minus 6x. Here I have a plus 2x. A minus 6x and a plus 2x is a minus 4x. And 2 times a minus 2 is a minus 4. And this is now over the common denominator of 3 times x plus 2 times x minus 2. The next fraction, x minus 2 over x plus 2 times x minus 2. Again, we're going to ignore that we could reduce this right now. Let's just notice that it's missing a common factor of 3. Please know that I need to multiply the whole numerator by that 3 in order to write an equivalent expression. So I'll have x times 3 here, which is 3x, and 3 times a minus 2 is a minus 6, over the common denominator of 3 times x plus 2 times x minus 2. And I'm ready to add. Well, this 3x squared doesn't have a like term over here, so I'm just going to include that. This minus 4x and this plus 3x combined to be a minus 1x. And finally, a minus 4 and a minus 6 combined to be a minus 10 over 3 times x plus 2 times x minus 2. Now I could stop here, but I have a feeling that I shouldn't. I have a feeling that this numerator right here could be factored into the product of two binomials. And I'll bet one of them is going to be x plus 2 or x minus 2. I'm not going to have space in or time here to show you the alternative method of factoring this. I'm going to do this by trial and error in my head, and I'm hopefully going to come up with the right response the first time. I know that I need a 3x and an x to factor this into the product of two binomials. I need that in front. I know that I probably need, for this to work, a 5 and a 2 over here. I'm guessing that I better put the 5 here and the 2 here because I think I need this x associated with a 2 in order to simplify it up here. Finally, my inner of 5x and my outer of 6x, I need them to subtract to be a minus 1x. So it looks like I'm leaving my minus sign here and my plus sign here. Let's just check it one more time. 5x minus 6x is a minus 1x. And I do have 5 times a minus 2 is that minus 10. All of this is over 3 times x plus 2 times x minus 2. And I see at the very end, and I need to catch this in any problem, that if I can reduce this, I should. My answer to this problem is in the numerator 3x plus 5, in the denominator 3 over x plus 2. I'm going to box that in so you can see that more clearly. It's complete. This is is the last problem that we're going to solve when adding and subtracting rational expressions. Again, I'd like to remind you to refer in Course Compass to the Assignments area. Click on the Assignments button, and then about the fourth or fifth item down, it either says Supplemental Material from your instructor or Important, Very Important Material from your instructor. Open that folder and click on the appropriate chapter. Introductory Algebra students, that's Chapter 6. Intermediate Algebra students, that's Chapter 5. That we're studying here, right here, rational expressions. There's a lot more material in intermediate algebra to follow. Introductory algebra, this is almost the conclusion. We'll be solving rational equations for both here in the next 10-minute clip or so. But this will be the last problem that we'll solve when it comes to adding and subtracting rational expressions. I'd like to just remind you that the steps involved, and this is also posted in Course Compass in a short summary sheet for this chapter. It says that you should factor the denominators first, then you should find a least common denominator. Once you've done that, you need to multiply these two fractions by the part or parts that's missing in order to get a common denominator in each. You'll multiply only the numerators together. You'll leave the denominators in their factored form. Finally, you will add and or subtract, depending on what you're doing, the numerators only. Put them over a common denominator. And if you find at the very end that you can factor that numerator and reduce it with something in the denominator, you should. Let's look at this problem. I have trinomials in each of these denominators, so I'm going to factor them. This one will be a minus 3 times a plus 2, and this one will factor into a plus 2 times a plus 2. This one's kind of interesting. It's very important to watch this. The least common denominator in this must include each factor the greatest number of times that it occurs. A plus 2 as a binomial occurs here twice. A plus 2 occurs here once. I need to put a plus 2 in my common denominator 2 times. Finally, a minus 3 occurs here once. It does not occur here at all. It must be in my common denominator, a minus 3. Finally, I need to take this fraction and get another a plus 2 in the denominator, and I need to take this fraction and get the a minus 3 in the denominator. Let's do that. Again, like we said a minute ago, this fraction is lacking a binomial a plus 2. So I need to multiply top and bottom in order to get that common denominator by a plus 2. And again, you will only multiply the numerators. So I'll have 10a plus 20 over the common denominator of a minus 3 times a plus 2 times a plus 2. And next, I'm going to take the 3a over a plus 2 times a plus 2, and it needs to be multiplied by a minus 3, top and bottom. Now, I can choose to distribute just a positive 3a times both of these terms, but since this is a monomial, I could also choose to distribute or look at this as plus a negative 3a and get this into an addition problem right away. And I think I'll do that. A negative 3a times a is a minus 3a squared, and a minus 3a times a minus 3 is a positive 9a. Over the a minus 3 times the a plus 2 times the a plus 2. Next, I'm going to take and combine my like terms in the numerator. The 3a squared is all alone. I'll have a minus 3a squared. The 9a and the 10a is a positive 19a. And finally, a positive 20 at the end. The binomials downstairs, the common denominator, a minus 3 times a plus 2 times a plus 2. I'm looking at that to kind of surmise whether or not I think this trinomial can be factored into the product of two binomials, where I might end up being able to reduce something from downstairs. Noticing that I have just 3's and 2's at the back end of each of these binomials, I know that two numbers whose product is 20 include 4 and 5, so that's not there. They include 2 and 10. So, you know, I do have the possibility here to have to work with that. And I think what I'm going to have to do is I'm going to have to check this out on the next screen. The previous problem ended with an answer like this. I have since checked out to determine whether or not the numerator can factor, and this is what I discovered. First of all, I don't like to factor a trinomial that's got a negative sign in front of the first term. So I like to factor a -1 out of that trinomial. So in doing that, I'll have a positive 3a squared. This positive 19 will become a minus 19a. And this positive 20 will become a minus 20. What I did, in an effort to check out that numerator to see if it would factor, is I used the alternative method. The alternative method says take the product of the 3 times the negative 20. That product is a negative 60. And then look and see if you can find two numbers whose product is a negative 60 that add, or whose sum is a negative 19. These two numbers have to be opposites in sign, so I could have 1 times a negative 60, or a -1 times 60. I do know that the bigger number has to be negative, absolute value. 2 times 30, those don't add to be a negative 19. 3 times 20, those right there add to be a negative 17. Finally, 4 times 15, but 4 and a negative 15 add to be a negative 11. I was thinking that might be it, that they might add to be a negative 19. That's not going to work. 5 goes into 60 12 times. Those don't add to be a negative 19. 6 goes into 60 10 times, and I'm going in the wrong direction at this point. These numbers, their sum is becoming greater, if you will, not so negative. While I could keep trying this, and actually I think I've hit my limit. Those are my factors of 60. None of those will add to be a negative 19. That means this cannot be factored. That means this answer was good as it was, but I did have to check it out.